Okay, so the foundation of all of calculus is the idea of a limit. So before we get into our mathematical definition of what a limit is, let me just kind of give you my non-mathematical definition. All right, so when we talk about a limit, that means we get really, really close to but do not equal. Okay, so this is our foundation, the concept of a limit. So even when I start introducing all of the mathematical ideas here in just a moment, I want you to remember as we go through this unit that when we talk about doing the limit of a function or calculating a limit, what we mean is we're going to get really, really close to, but do not equal. Now, let me be a little more precise with that. When I say get really, really close to, that means as the x value, as x gets really, really close to a value. Okay, so as you let the x number, the x value, get really, really close to equaling some number, some value, then the question, or what we're trying to figure out is, then what does the y value get really, really close to? Okay, so when we're doing a limit, what I'm asking you is, if I let an x value get really, really close to some number, I need you to tell me what is the y value getting really, really close to. And this is the extremely important part. It sounds simple to begin with, or hopefully it's going to sound simple, but we're letting the x get really, really close to, x gets really, really close to, but does not equal. This is the important part. We do not let x equal the number, right? So that's going to be a very important idea here in a few minutes or later in the unit. So when the x gets really, really close to it, the question of doing a limit is, what does the y value? So the answer to a limit is to tell me the function value or the y value. What does that get really, really close to, okay? And when we're talking about the y value, it can equal a value, a number, but it does not have to. All I really need to know is, what does it get really, 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 really close to? So you do not have to equal a number, but you have to get really, really close to. And again, before I get into doing this in the mathematical context, let me ask you this question. So maybe you have a credit card. So if I was your mom or dad and I said, all right, I'm going to give you a credit card, I would put a spending limit on you so that you couldn't spend more money than I have. So let's say maybe that your spending limit is $1,000, right? So I trust you to go out and buy things on your credit card, but I gave you a spending limit of $1,000. So that means you could spend, and this is the idea I want to kind of come into, you can spend $999.99, right? So you can spend all the way up to $999.99. Well, what are you getting really, really close to now? You are getting really, really close to $1,000, which is your spending limit, or the speed limit when you are driving. If the speed limit is 70 miles per hour, theoretically you could drive 69.99999 miles per hour, but you get really, really close to 70. So the idea of a limit is, what do we let the x value get really, really close to? And then as that happens, what does the y value get really, really close to? All right, so let's see if we can do this and do some of the notation. All right, so the first thing is the way that we abbreviate the word limit. Okay, so obviously we're going to abbreviate limit with LIM. So that's telling you you're going to take the limit. You have to take the limit of something. So this is the function that we want to take the limit of. Okay, so I'm taking the limit of function f of x, or I could take the limit of function g of x. So whatever function that you want to take the limit of. And then you did this in Algebra 2, maybe in pre-cal a little bit also. So remember this notation with the arrow. So that's telling me as the x value approaches. So our arrow in math tells us that as x approaches, and in this particular case, we are approaching infinity. So what does that mean? So that just like our non-mathematical definition from just a moment ago, that means as x gets really, really close to, but not equal, and in this particular problem, we're getting really, really close to infinity, then the answer to the limit, okay, so this is the big idea when you're actually going to do a limit. So the answer, your job is to do what? Your job is to tell me what does the y value, or the f of x, remember f of x is another name for y, the y value. So what does the y value, which is the function value, get close to? And then that's the question we're trying to answer. All right, so this first time we're going to approach this with our graph. All right, so let me pull up our graph and we can kind of take a look at this, and we're going to do this first problem right here. All right, so as we pull this up, so here's my function f of x, and notice right now I've got a x value that can move around, and as the x value moves around, my red y value, the function value, is changing also. All right, so this is sort of a complicated looking function, but we know it's a function because if we were to do the vertical line test, any vertical line we put on this graph, it only touches the graph in one single spot, so this is a function, so we have to have functions. All right, so the problem we were trying to do just a second ago, let me come back to the screen real quick. So we want to answer this question right here. As the x value approaches infinity, so as we let x get really, really close to infinity, all right, well, what does that mean on the graph? Well, that means the x value has to move farther and farther to the right because that's the infinity. And notice, as my x is changing, the y value, the function value, what that graph looks like, the y value changes. So as I keep letting the x get closer and closer to infinity, as I move it out this way, and let me slide my graph over just a hair. So as we start moving this as far to the right as we possibly can, the answer to a limit is to tell me not what the y value equals, but to tell me what does y get really, really close to. The idea of a limit is you do not have to equal something, you just have to be getting really, really close to it. So what would we say that this y value over here, as we move the x closer to infinity, farther to the right, what does it look like the y value, the f of x value, is getting really close to? Well, it looks like it's getting close to that horizontal line, which has the value k. So the answer to my limit would be k. And I'm using variables for specific values, but that would be some number like maybe it's 10 or 11 or 7, whatever that positive y value is. So on this graph, what we are seeing is that the graph, as x goes way out to the right, as x gets closer and closer to infinity, the y value is getting closer and closer to the horizontal line, y value equals k. So whatever that is, k is a specific number, but we would say the limit equals k. And notice, this is leveling off. Does it look like it actually ever touches k? So the y is not equaling k. It doesn't have to equal. It just has to get closer and closer and closer. And then the way to kind of think of a limit is sort of like rounding. So if I said, let's say that k value was 8, and we would say that, where we're at right now, we're a little bit lower than that. So maybe the number would be 7.9999999. So instead of saying that it's 7.99999, we say that's really, really close to the number 8. Even though we're not touching the number k, we would still say that the limit approaches k. The answer to the limit is k. All right, so let's see if we can do this second one over here. And notice this is the same thing. The only thing that's changing is we're going to let x approach negative infinity. And what does that mean? That means let the x value go way out to the left, and then the answer to the limit is to tell me what the y value, what the f of x gets really, really close to. It does not have to equal, it just has to get really, really close to it. All right, so if we go back to our graph, so instead of my x being on the far right now, we need to let x approach negative infinity. So start moving your x value farther and farther to the left. And let me scroll my graph over again. So as we go out as far as we can on the graph, way out here, what does it look like? The y value, my red point, the y, the f of x value, what is it getting closer and closer to equaling? Well, it's getting closer and closer to this horizontal line that has the value j. So we would say the answer to this one is j. And again, the big idea, the y value gets really, really close. The number, in this case, j, right? So j would be some negative number, -5, -10, whatever that number happens to be. So as the x goes out toward negative infinity, as x gets closer and closer to negative infinity, the limit of f of x approaches or gets really, really close to j. And again, looking at the graph, we are not touching j. It doesn't look like we're ever going to touch it, but we get really, really close to j, and that's the idea of a limit. What are you getting really, really close to? All right, let's go back and talk about some terminology now. All right, so there's different types of limits. So those first two, we're doing limits at infinity, positive infinity or negative infinity. So now what we're going to talk about is what we refer to as a one-sided limit. All right, so whenever you see a little plus sign or a little negative sign in the superscript. So superscript means above the number, subscript means below the number. So this is in the superscript. All right, so that tells you that you're going to be dealing with it, what we refer to as a one-sided limit. All right, so the way that I always kind of remember this, if you think about our number line for a second. So I see a plus sign and I see a negative sign. What separates the pluses from the minus would be 0. So everything on the right of 0 is a positive number. Everything on the left of 0 is a negative number. So whenever you see this symbol, A represents a number, a specific value. Okay, so A is just some number. So what, again, this part of the notation is telling me, so right here, this means X gets really, really close to the number A, right? So I'm going to let X get closer and closer and closer to equaling A, but does not equal, X does not equal the number A, it just gets really, really close to it. And then because you see the little positive sign up here, that means that it is approaching, so it approaches the number A, and positives are on the right of 0, so that means we're approaching A from the right. So we approach the value X equals A from the right-hand side. So the way to think of this is we're going to be moving toward the number A, wherever this A is, from right to left. We are moving from the right-hand side closer and closer to A, and we always stay on the right-hand side, so we're going to get closer and closer to the point A from the right. All right, let's take a look at our graph and see what the actual answer is. All right, so here's my X value way over here, and then I see where A is. So because this is a right-hand limit, the first thing I'm going to do, let me slide my graph, or slide my X value somewhere to the right of X equals A, and then remember what we're doing. I'm going to let the X value get closer and closer to A, and the f of X is changing. So as I keep moving the X value closer and closer to X equals A, but it does not equal, X does not equal A, X is getting really, really close to A, but staying on the right-hand side, because this is what we refer to as a right-hand limit, where do you see the Y value going? So right here, the Y value is right here at G, basically, right? And then up here, it moves up to around F, and then it goes to K, basically. But as I move closer and closer, it keeps going up, and it looks like the graph is going off the graph paper up and up and up. So what number would be the very highest point on our graph? So that looks like it is getting closer to infinity. And again, this is why we stress the definition. So our answer, right? What does the y value approach, right? The answer to a limit is y gets close to, and in this particular case, it's going up and up forever and ever, so y is getting close to positive infinity. When we do a limit, the x value never equals the number, and then when we answer the question, what is y, we're saying what does y get close to? Y does not have to equal that, because you can't equal infinity, but the y is getting bigger and bigger and bigger. It is approaching or getting close to infinity. So the answer to this one, our right-hand limit at a, would be positive infinity. All right, look on the one on the left, or sorry, on the far right. So right here, we're approaching the left-hand limit. And that means we're going to be moving from the left-hand side, staying on the left, moving closer and closer to a on the left-hand side. All right, so the positive symbol means right-hand limit, and you'll see me abbreviate that RHL. The negative symbol means left-hand limit, so you'll see me abbreviate that LHL. So positive sign has nothing to do with where the number A is. It just means positive is on the right, negative is on the left. And again, the big idea, as we let the x get closer and closer and closer, what does the y value get closer and closer to? So let's see if we can look at our graph again. So this time I'm going to take my x value, line it up on the left-hand side to the left of x equals a. So when I'm at this location, I can see my y value is right here. Okay, so now let me come back right here as we move. Oops. So as I move it, the y value changes. And as I start to get really, 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 really close, but not equal, x does not equal a, but if I get it as close as I can possibly get it without it actually equaling a, what do you see the y value getting really, really close to? So notice, it's getting really, really close to that open circle. And what did that open circle mean in Algebra 2? That meant there was a hole in the graph. There is no y value there, so there is a missing y value at that spot. But what is the red circle, the red point for f of x, getting really, really close to? It's getting close to this open circle, and that open circle is located, if you look across, at the y value g. So even though there is a missing point there, there is no y value at x equals a, I can still say that the answer to the limit, so when we look at our graph, right, the answer to the limit is g. You do not have to equal the value, you just have to get close. So when you have that hole, you have a missing value. Y does not equal anything at x equals a. There is no y value at x equals a. But when we do a limit, we're not trying to answer the question, what does y equal? We're trying to answer the question, what does the y value get really, really close to? So it's getting closer and closer to the value g. So even though it doesn't equal that, we would say that the limit is equal to g. All right? So that's a one-sided limit on the left. We have a one-sided limit on the right when you see the plus sign. So now let's talk about when you do not see. So if you do not see a plus sign, so if there's no plus or minus symbol in the limit notation, that means we're not doing a one-sided limit, we're doing a two-sided limit. So our definition for a two-sided limit means the x approaches a, gets closer and closer and closer. And then since it's a two-sided limit, that means from both sides, from both the left and the right-hand side. And the most important definition when we're doing limits, so we've got our one-sided limit on the right, we've got our one-sided limit on the left. So the definition of a two-sided limit, for the two-sided limit to have an answer, or we say to exist in calculus, this means that the limit on the left-hand side has to equal the limit on the right-hand side. Okay, so for my two-sided limit to exist, the limit on the left has to equal the limit on the right. And if both of those are equal, if this one on the left equals the one on the right, then we say the limit exists, and whatever they equal is what the two-sided limit equals. If these are not equal to each other, then we would say the limit does not exist, and we'll talk about how we do that. So let's look at the graph real quick. All right, so let me slide my point. Let's talk about the left-hand limit, right? We just did that. So as we get closer and closer from the left, we're getting close to G. As we move closer and closer to x equals a on the right, we're going up to infinity. So if we put in our answers from just a second ago, so on the left-hand side, the answer was G. On the right-hand side, the answer is infinity. G does not equal infinity. The number G, whatever that y value is, 3, 4, 5, whatever that actual y value would represent, it is not equal to infinity. So when these two do not equal each other, we say that the limit does not exist. Or sometimes on AP Calculus, you might see it written this way, non-existent. That means it does not exist, so it's non-existent. So if the left-hand limit does not equal the right-hand limit, then the two-sided limit does not exist. If the left and right equal each other, then you use that number. All right, so let's see if we can kind of put these together and go through. All right, so first question you should always ask yourself when you're doing a limit is, what type of limit do I have? All right, so get in the habit, like, not that you're going to say it out loud, but ask yourself in your head, what type of limit is this? You have to know when you look at it, because that informs you how you're going to actually answer the question. So when I look at this one, since there is no plus or minus symbol, this tells me that this is a two-sided limit. And the moment I see that it is a two-sided limit, every single time you do any question that talks about being a two-sided limit, you've got to start asking yourself, the limit on the left equaling the limit on the right. Does the left-hand limit equal the right-hand limit? If they are not equal, then you're going to always say D and E. If they're equal to each other, then you say that answer. All right, so the limit on the left has to equal the limit on the right. So if we look at our graph again, all right, so we're approaching 0. So the x value is getting closer and closer to 0. And notice I'm doing the left-hand limit. So I'm on the left-hand side of 0, getting closer and closer and closer to x equaling 0. And if I make it as close as possible, what does it look like my f of x is equaling? Well, it looks like we're going to land right on that black point. And so that value is h. So my left-hand limit is equal to h. That's what we're getting closer and closer to with the y value. All right, let me move my x value over here to the right. And as I move closer and closer towards 0, but I stay on the right-hand side, I'm doing the right-hand limit. So as I get it as close to 0 as I possibly can, so again, the red circle is getting really, really close to that black circle. So the answer on that one would also be h. So if my left-hand limit is h and my right-hand limit is h, then that means the two-sided limit should equal h. So the answer to this question should be h. The left and the right approach the same number, h. All right, see if you can do the next one. Ask yourself what kind of limit this is, and then, excuse me, see if you can actually get the right answer. Pause the video if you want to take a moment. So if we look at our graph real quick, so we're doing the limit as x approaches b with a plus sign. So the limit as x approaches b with a plus sign. So the plus sign tells me it's a right-hand limit. As we come closer and closer to b from the right, then let me see if I can scroll down a little bit. So it looks like as we get closer and closer to b, the graph just goes down and down and down forever in a negative direction. So as we keep going down and down and down, what would that mean the answer is? So that means we're equaling negative infinity. All right, if we do the second question on this other side, Notice it's a left-hand limit. So this was our right-hand limit. So now if we do the left-hand limit, that means we approach B. So let me slide away from B. I have to be on the left-hand side, and as I slowly move the X value closer, what's happening to the Y value? The Y value is getting really, really close to the X-axis. So notice, again, we have an open circle right here, so there is no Y value at that location. But what is the X getting close to? When X gets close to B on the left, we are getting close to this open circle, and because it's on the X-axis, that means the Y value is 0. So this answer should be 0. Now, let me go back and highlight one thing real quick just to make sure you're understanding this. So notice, if I put the point at X equals B, okay, so it disappears because there's a hole there. But what is the actual Y value? The Y value would be this spot right here. That's your closed circle. So remember, like in Algebra 2 and Pre-Cal, if I ever say, like, what is F of, that means find the point. The Y value actually equals the number G when X equals B. But our big definition from the very first page was when we do a limit, X gets really, really, really close to, but not equal. You do not let X equal the number. You let X get really, really close to the number. And then you tell me what does the Y value get close to. So again, as I move this point closer and closer, all these Y values are coming down toward the X-axis, which means they are getting really, really close to 0. So looking back up here, we've got our left-hand limit, we've got our right-hand limit. So when I look at this one right here, this is a two-sided limit. The moment I ask you about a two-sided limit, you have to start thinking, does the left-hand limit equal the right-hand limit? Are they equal to each other? Well, my right-hand limit is negative infinity. My left-hand limit is 0. Those are not equal. So our final answer, when they're not equal to each other, we write D and E, does not exist, non-existent. All right. Again, if you want to try this next one, you can pause the video if you want to. Ask yourself what kind of limit, and then see if you can get the right answer, and I'll catch up with you in just a second. Sorry, wrong page. All right, so as we approach C, so on the left-hand side, because I'm on the left, if I can get it as close as I can, as X approaches C on the left, as I get closer and closer to equaling C on the left, where do I see the red Y value going to? The red Y value appears to get closer and closer again to the open circle, which has a Y value of P. So because this is a two-sided limit, that means we're going to check to see, does the left-hand limit equal the right-hand limit? Okay, we're checking to see if that's true. And we just looked at the left-hand limit, and that was equal to P. So on the left, the answer is P. All right, if I want to check the right-hand limit, I move my X value somewhere to the right of C. And then as I move it closer and closer, as X gets closer and closer to C, let me slide my graph up a little bit. So what are we getting closer and closer to equaling here? Again, notice, excuse me, we're getting closer and closer to C on the right, and it's getting closer and closer to that open circle at the top, which has a Y value of F. So my right-hand limit would be F. Well, the Y value P and the Y value F are not the same, so these do not equal each other. So that tells me that my two-sided limit, again, does not exist. The left-hand limit and the right-hand limit do not equal each other. All right. Does that seem like it's making sense to you? So let's check this next one. I look at my limit. Very first thing I ask myself, what kind of limit? No plus or minus sign, so that means it's a two-sided limit. I have to check both the left-hand limit and the right-hand limit. Check to see, are those equal to each other? So my left-hand limit and my right-hand limit, are they the same? And notice this time we're approaching E. All right, so I'm going to do the left-hand limit first. And let me slide over this way some. All right, so as we approach from the left, where do you see this red Y value going? It's getting closer and closer to that open circle right there. And again, that open circle is on the x-axis, so that's a Y value of 0. So as we get closer and closer to the x value E, the Y value is approaching. It does not equal, because there's an open circle. You cannot equal anything in an open circle, but we don't care about trying to equal it. We're just asking ourselves, what do we get really, really close to? So we're getting close to 0. All right, look back at the graph again. Let me move my point on the right-hand side. So the Y value is way up there, close to that line at K. And as I move closer and closer to x equaling E, get x close to E, on the right, and again, what do we see that it's really, really close to equaling? It's close to equaling that open circle, which again is a Y value of 0. So if the left-hand limit is 0 and the right-hand limit is 0, that means my two-sided limit is equal to 0. And put a big star by this one. This is really, really important. So notice right here, we are saying that the limit of the function on both the left and the right of x equals E is 0, even though there is no actual Y value at x equals E. At x equals E, we are undefined. Because we have an open circle, there is no Y value at x equals E. So when you look back at our graph, all I see, let me slide this out of the way so we can get a little bit better view, there is no actual point, no closed circle when x is equal to E. This is a specific hole in the graph, which means it is an undefined value. X cannot equal E in this graph. But when we do a limit, we're not saying what's the Y value when x equals E. We're saying what does the Y value get close to when x gets close to E. So as we get closer and closer, but not equal, we're getting close to 0. As we get closer and closer, but not equal. So even though right here, there is no Y value, I don't see the red circle anymore. So even though there's no Y value, the limit still exists. Because a limit, if you think of it as like rounding, if I tell you, like, again, let's say that this is negative 0.000001 and positive 0.00000001, well, what are both of those numbers close to? They're really, really close to equaling 0. That is the idea of a limit. Just let the x get really, really close and tell me what does the Y value get really, really close to. All right, so now, back to Algebra 2 and pre-calc. There's no limit on this problem. So when it just says f of, this is important, and it's just reviewing something you already know. So this means when x equals 0, what does the Y value equal? So where I cannot round, I'm not doing any approximating or rounding, to the number. When you have function notation, this is the shorthand symbol that means when the x is exactly equal to 0, what does the Y value exactly equal? All right, so if we go back to our graph, when the x is, when our x value is equal to 0, so let me slide this guy. So when x is actually on 0, I don't know if you can still see the little red lines showing up through there, but my Y value is exactly, the closed circle is exactly at H. So when I answer this question, when x is exactly equal to 0, the Y value is exactly equal to H. All right, and again, if you think you understand the next one right here, f of b, pause the video and see if you can answer this one real quick. So now if I look at f of b, so let me hold this guy out for a second. So when I'm at x equals b, there's an open circle at that location. So I'm not looking for the open circle. I want to know when x is exactly equal to b, what does the y value exactly equal? And anytime I'm asking you for a function value, the easy way to remember this, it has to always be the closed circle, right? The actual function, but the actual y value. So when x is equal to b, then the y value is at g. All right, and then f of a, go back to our graph real quick. I think our point's kind of a little messed up. There we go. All right, so at x equals a, so the right-hand limit went out to infinity, so you can't equal infinity. The left-hand limit came to the open circle. There's no y value there. So when you try to let x equal a, when x is exactly equal to a, I do not see a closed circle anywhere on the graph. So remember, our dotted line is showing us what's happening exactly at x equals a. So since there is no closed circle, you're not seeing a closed circle anywhere, then we would say the point is undefined. Okay, so not a huge deal, but sometimes I've seen on tests, like in college or on the AP exam. So a limit, when you're answering a limit question, a limit can be a does not exist. If it's a function value, right? So this means when x equals a, y equals what, right? Well, there's no y value, so it's not defined. So for a function value, we use the terminology, the function is undefined. For a limit, we use the terminology does not exist. Okay, so if the closed circle, anytime you see the function value on a graph, you are looking for the closed circle. If you don't see a closed circle at that location, then you would say it's undefined. All right, and then my last thing right here for us on reading the graphs and doing limits. All right, is there a difference, or explain the difference between the limit notation and the function notation? All right, so if I want to explain the difference between the limit, right? So the limit means as x gets close, but not equal to, in this case, it would be the number c, right? So as x gets really, really, really close, but does not equal the number c, I'm asking the question, what does the y value, and again, not equal, but what does the y value approach? What's it get really, really close to, right? The answer to the limit is to tell me what the y value approaches. What does it get really, really close to? When you are doing function notation, this means find the exact y value when x is exactly equal to c. So you're not letting x get close. X has to equal exactly that number. And then you can't tell me what y gets close to. You have to tell me what y is exactly equal to. And on a graph, the easy way to remember this, you're just always looking for the closed circle. So if you do not have a closed circle at that location, you would say undefined. If you have a closed circle, then you just tell me what that y value equals. All right, is that kind of making sense? All right, so next part of our lesson, we're going to discuss the calculus definition for a horizontal and a vertical asymptote. So we've learned about these concepts in Algebra 1, Algebra 2, and Pre-Cal. So now what we're going to talk about is how do we apply the calculus definition for a horizontal asymptote and a vertical asymptote. All right, so let's look at a horizontal asymptote first. All right, so our definition says, if you do the limit as x approaches negative infinity of your function, and that answer is equal to a number, then y equals the number is a horizontal asymptote. So the definition of a horizontal asymptote says you have to evaluate a limit at negative infinity. So this is the really important idea. You're evaluating your limit at negative infinity, and the answer has to be an actual number. So you cannot get infinity for an answer, not positive infinity or negative infinity, but you have to get an actual number value. All right, there's a second definition. So or, and then we evaluate a second limit. The limit as x approaches positive infinity. And again, if the answer to that limit is a number value, an actual real number value, then the definition says that number is a horizontal asymptote. So the only way to have a horizontal asymptote is you check the limit at negative infinity, which is the far left side of the graph, and you check the limit at positive infinity, which is the far right side of the graph. And if those answers are number values, when you evaluate your limit, if you actually get a number, then that's the definition of a horizontal asymptote. All right, so I've got the graph right here. So let's see if we can do this one without looking at the computer image and just look at the single image. All right, so if we start moving the x value as far as we can on the x-axis so that we start approaching negative infinity, what would be happening to the function value, the y value? So I start here, I move. As I keep moving over, what are these y values doing? They are getting closer and closer to approaching this line, which has a y value of j. So my answer, the limit as x approaches negative infinity, we did this earlier, would equal j. Well, the number j, we're using a variable, but it's representing a number. So if the limit at negative infinity equals j, then we would say we have a horizontal asymptote at, and remember the definition of a horizontal line is y equals the number. So we would say our horizontal asymptote is at y equals the number j. All right, you turn around and do the exact same thing for the right side, the far right of the graph. So this time we're going to take the limit as x approaches positive infinity. So if we start letting the x value come farther and farther to the right, so way out here at positive infinity, as far out to the right as we can go, what are we getting for the y value? So as I start picking, let's say I'm right here, so these y values come down as you move farther and farther to the right. And then notice they're all leveling out right here. So what are we approaching? We're approaching the y value k. So the answer to our limit is k, which again is a number. So that tells us, because the limit at infinity is equal to k, that tells me I have a second horizontal asymptote at y equals k. So we get two different horizontal asymptotes on here. And then think about this for a second. Is there a maximum for the number of horizontal asymptotes I can get? Like, is there more than two? Well, that doesn't really make any sense, right? Because we can only do two limits. So what can happen when we're doing our horizontal asymptotes, you can either have 0, 1, or 2 total horizontal asymptotes. So on a lot of graphs, you may not get a horizontal asymptote at all. So an example of that is if you're doing a limit. So let's say we're looking at the graph y equals x squared, right? So if I take the limit as x approaches negative infinity of f of x, so as we move out to the left, what do we see the y values doing? Going to positive infinity. If I do the limit as x approaches positive infinity, the far right, what is the graph doing? It's going up forever and ever. So again, positive infinity. I did not get a number for either limit. The limit at negative infinity and the limit at infinity are both infinity. So that means there is no horizontal asymptote. And you can look at the graph and see the graph, when we go way out to the right and way out to the left, is not leveling off like a horizontal line. It's going up to the infinity. So that makes sense. There's no horizontal asymptote. A lot of times when you do an actual problem, you should get one horizontal asymptote. So most common answers are either you get 0 or 1, but every once in a while it is possible the maximum number of horizontal asymptotes has to be 2, because you can only check two different limits. You can only check the limit at negative infinity and the limit at positive infinity. All right. Now, the way to think about a vertical asymptote, it's kind of the reverse. All right, so the way the vertical asymptote does, instead of checking the limit at one of the infinities, we're going to take a limit as x approaches a specific value. So we do the limit on the left of a, and if the answer either becomes positive infinity or negative infinity, then, and because this is a vertical asymptote, a vertical line is x equals a number, so x equals a is a vertical asymptote. So instead of approaching infinity and getting a number answer, we're going to reverse it. We're going to approach a specific number right here, and then this is a left-hand limit, right? Approach it from the left, and then I don't care what the answer is as long as the answer is one of the infinities. So instead of doing the limit at the infinity and getting a number answer, that's our horizontal asymptote, we're reversing it. We're going to do a limit at a number, and the answer has to be one of the infinities. And then again, there's a giant or statement here. So that's one way you could be a vertical asymptote, or you could also do the right-hand limit. So as you approach a from the right, and again, I don't care which answer you get, as long as the answer to the limit is one of the infinities, then again, this is telling me that x equals a is a vertical asymptote. All right, so you have four different ways. You could do a left-hand limit and get positive infinity, a left-hand limit, get negative infinity, right-hand limit and the answer is infinity, or a right-hand limit and the answer is negative infinity. And you just need one of those to be true. And if one of those is true, then x equals a is a vertical asymptote. Right, so to do our vertical asymptote, we need to check a specific value and try to find a place where we see either the left-hand limit or the right-hand limit approaching an infinity. All right, so if you kind of come back over here, we've already done this one earlier, but if we move x approaching a from the right-hand side, let me see if I can scroll up a little bit so we can see that a little bit better. So as x approaches a from the right-hand side, our graph is going up and up and up, and it just goes off the page, up off the page. So since the right-hand limit at x equals a goes to positive infinity, that would be a definition of a vertical asymptote, all right? So the way we would write this up, so we would say the limit as x approaches a from the right-hand side of our function f of x is equal to infinity. So x equals a is a vertical asymptote. And remember, x equals a number is a vertical line, y equals a number is a horizontal line. All right, so we have one vertical asymptote. Let's check the graph again and see if there's any other ones. All right, so maybe let's take a look over here at point C. So let me scroll down a little bit. So if I come and check out point C, on the left-hand limit, we are getting really close to point P, right? Getting closer and closer to P, which is not infinity. If we check the right-hand limit, we're getting closer and closer to point F, which is not the infinity. So even though I'm seeing a dotted line there and something weird is happening at x equals c, that's not a vertical asymptote. All right, so are there any other places we should check? Let's go back and maybe look at point B. So notice if I do the right-hand limit as we approach B from the right, let me scroll down a little bit just to make sure. What is our graph doing? It's going down forever and ever. So on the right-hand side of B, the answer is negative infinity. So when I do a limit at a number, either on the left-hand side or the right-hand side, so I'm now getting a second vertical asymptote. So the limit as x approaches B on the right is equaling negative infinity. So that means x equals B, the vertical line, x equals B is a vertical asymptote. You do not need both the left and the right to go to an infinity. You need one or the other. So any place where we see a one-sided limit at a number value have an answer that is either positive infinity or negative infinity, that's our calculus definition of vertical asymptote. All right, last thing I want to talk about is using doing limits from a table of values. All right, so this hopefully should be pretty straightforward also. So I've got a couple of tables of values, and then first thing we always do, like I said earlier, always ask yourself, what type of limit do I have? So when I look at this one, we're seeing the negative sign in the superscript. So that makes this a left-hand limit, right? So that means we're going to be approaching 2 from the left. So now that we actually have a number instead of like the A's and the B's and all that stuff on the last graph with letters, think about on the number. So if you're going to be on the left-hand side of 2, so we're over here and we have to get closer and closer to 2. So numerically, wouldn't that be like 1.5, 1.6, 1.7, 1.8? And then you would have 1.9 on the left-hand side. So the key, because you're seeing the negative sign, this is a left-hand limit, so you have to be approaching 2 from the left. So notice, I start at 1.9, which is right here, and then I move even closer, and I'm going to move it up to 1.99 and 1.999. So as the x values start to approach 2, right? You get it as close as possible, but not equal to 2. Get really, really close. So 1.9, 1.99, 1.999. So as we get closer and closer to 2, but we are staying on the left-hand side of 2, what does the y value get close to? So on our first point, we're at negative 6.6, negative 6.92, negative 6.95. So remember I said earlier it's kind of like rounding. So do you see a pattern of what the numbers are getting really, really close to? So this is approximately equal to negative 7. You are getting, as we move closer and closer to 2 with the x value, the y value is getting closer and closer to being the number negative 7. So the answer to the limit would now be negative 7. My left-hand limit is equal to negative 7. All right, if we're going to do the right-hand limit, notice the plus sign tells us that it's a right-hand limit. So that means we're going to approach 2 from the right. So this is my right-hand limit. So over here, I might have the number 2.5 and then 2.4. So as we move in this direction, eventually we'll get to 2.1. So that's where we're starting at 2.1. A little bit closer would be 2.01. So as we move closer and closer to letting the x value get really, really close to equaling 2, but not quite 2, and it has to stay on the right-hand side because this is a right-hand limit. So then we do the same thing. We ask ourselves, what is the y value doing? So we start here at negative 7.8. As we move x in, the y changes, the y changes, the y changes. What do you see that the y value is getting really, really close to equaling? Negative 7.0001 would be really, really close to negative 7. So we say that the limit is negative 7. So all I'm going to do when I look at a table is find the pattern of what the y value is approaching as x gets closer and closer to the number, and either on the left-hand side or the right-hand side. All right, so now take a look at our last one right here on this problem. What type of limit do we have? If there's no plus or minus sign, that is a two-sided limit. So the very first thing we always have to ask ourselves when we're doing a two-sided limit, does the left-hand limit equal the right-hand limit? Well, yes, they're both equal to negative 7. So if they're both the same, then the two-sided limit is the same answer. All right. See if you can try this one on your own, and then pause the video, and I'll catch up with you here in just a minute. So hopefully you had a second to try the problem, and let's see if you got it right now. All right, so again, I see the negative sign on the number. This is telling me it's a left-hand limit. Now, because you are approaching negative 10, so the negatives are a little harder, just not hard, but harder than the positive numbers. So think about on a number line real quick. If this is negative 10, you have to be on the left-hand side of negative 10. So on the left would be negative 11. So if I pick a number like negative 10.5, right? And then I can move a little bit closer to negative 10.1, which is where we see it starting. And I'm going to keep on moving in this direction. So I start here with the x value. We move a little closer, a little closer, a little closer. What are we getting really, really close to? The x value equaling negative 10, but we are on the left-hand side. We're over here on the left. So what does the y value do? So again, we start here for the y, And as we move the x down, what is the y doing? As the x gets closer and closer to negative 10, my y value is getting really, really close to 3, right? 2.9994 would be really, really close to 3. So my left-hand limit would equal 3, all right? The limit on the other side is a right-hand limit because we see the plus sign. So if we're going to approach it from the right, so we would come in this direction. So you'd be over here at negative 9, and then this would be negative 9.5, negative 9.9, right? So I'm moving in this direction. So this is where we start our x value, negative 9.9. We're going to move the x's closer and closer, but we stay on the right-hand side of the value, negative 10. So we're still on the right-hand side, but we're coming closer and closer to equaling negative 10. And as we move the x value closer and closer, what do we see the y value doing? So we start here, x moves down or closer, and what is my y value getting really, really close to equaling? 3. So if my left-hand limit equals 3, my right-hand limit equals 3, what does my two-sided limit have to equal? If those are both equal to 3, then my answer is 3. All right, so all we're doing numerically, so now that we actually see numbers, is remember, as x gets closer and closer to equaling the number, what is the y value getting closer and closer? Y does not have to equal the value, it just has to get really, really close. All right, I'm going to do one more with you, and then I want you to try this last one on your own. Oops, sorry, I went too far. All right, so all I did here was reverse the way the table looks. All right, so first thing I always do, ask myself, what type of limit do I have? So again, negative sign means this is a left-hand limit. All right, so we're approaching positive 4. And if you're coming from the left, if this is 3, then on the left-hand side should be like 3.9, and then the next one would be 3.99. Right, we're moving in this direction, so this is where we start on the left-hand side. So as I move the x closer and closer to equaling 4, this is x equals 4 right here, what do you see the y value doing? So your y value starts here, and then as you keep on moving the x's in, what are we getting really, really close to equaling? Negative 1.999, or sorry, negative 1.998 is really, really close to negative 2. You can see the numbers are starting to get closer and closer to equaling negative 2. All right, if you do the limit on the right-hand side, our right-hand limit. So again, 5 is over here. This would be like 4.5 moving in this direction. So if we're really, really close, we might start at 4.1. So I start here on the right-hand side, and I move in this direction so that the x is again getting closer and closer to 4. All right, well, what are my y values doing? So this is my starting y value, 7.8, 7.94, 7.996. What are we getting really, really close to equaling? Well, that is approaching the number 8. So I would say that my limit is equal to 8. I see the pattern of the y values getting closer and closer to equaling the number 8. All right, so when I come down to do our third limit, which is a two-sided limit, that means the left-hand limit has to equal the right-hand limit every single time. Well, our left-hand limit was negative 2. Our right-hand limit was 8, so that tells me this one needs to be D and E. If they're not the same, that means it does not exist, D and E. And then, like we talked about from the graph paper, what does the function mean? So this means when x equals 4, what does y equal? So when x is exactly equal to 4, what does the y value equal? It equals negative 2. So my limit answer can be different than the function value. That is perfectly fine. So you're just checking to see what the pattern is, and then anytime you're doing the function value, the f of, you're only looking for one single value that y equals when x equals that specific number. All right, so we got one last example. Pause the video and try this one on your own, and then we'll check it together here in just a minute. And hopefully you had a moment to try it. So again, left-hand limit, I almost always format mine where I put the left on the left-hand side. Doesn't have to be that way, so pay attention. All right, so again, what number are we approaching? 7. So if this is 7, and you're going to be on the left-hand side of 7, so here's 6, so what number would be there? So we could start it at, in this particular problem, right? Starting at 6.88, and then we're moving to 6.97, moving in this direction. So as we move in closer and closer to x equals 7, so as we get really, really close for the x value to equal 7, what are our y values doing? So we start at 12.5, 12.9, 12.996. So what's our pattern? We're getting really, really close to 13. So our answer on the left should be the value 13. So the left-hand limit is going to 13. Let's try the right-hand limit. So again, something on the right of down here would be 8. Something in between those two might be something like 7.2. That's where, that's where I see this one starting. And then you move in a little bit closer, and now you're at 7.04. So as we move in, we are getting the x value to be closer and closer to 7, but from the right. So we are approaching 7 from the right. That's what a right-hand limit means. And then what are we doing with the y values? So we start right here, 2.87, 2.98, 2.995. What are we starting to get really, really close to? The number 3. So my right-hand limit would be the number 3. And again, our third limit is a two-sided limit because there's no plus or minus sign. Anytime we see a two-sided limit, we have to check to see, does the left-hand limit equal the right-hand limit? 13 does not equal 3. So this would be another example of D and E. And then anytime I'm doing the function value, I'm saying when x is exactly equal to 7, what does y exactly equal? So in this problem, it would equal 10. All right, hope that's pretty easy with the table. Let's try some homework.